Sorry for the short delay here. So we'll kind of pick up where we left off. And that was kind of talking about interaction terms. So we've got kind of this post. This is the one we were using last class. I uploaded a new do file. We'll kind of be using this one today. So it's the one that says kind of fall 2024 instead of the post one. I had some added code in there that I didn't have in the one that I uploaded last week that we'll be going through today and on Thursday. We've got the different data sets that we'll use and then our slides. So if I remember correctly, we left off thinking about, we had these differences in slope. And I think that I left off with this idea of, I don't think I hammered this too much, but we can start to identify differences in the effect of something on different groups. So I had this like looks or this beauty data set that we were using. We then said, okay, maybe when it comes to like wages, employers are treating the looks of male employees differently than female employees, and we can actually estimate to see whether or not that's the case. So how did we do that? Well, we included the group that we thought the effect might vary for. So this is females. We included the variable we want to know the effect of. This is looks or this beauty measure. And then we also included an interaction between the two. We said there's a couple different ways we can do this. We could create the variable and state ourselves. We could use kind of that double hashtag, right? We'll kind of look at that syntax here in a second in an actual do file. But either one, they would throw in an additional interaction term for us. And then beta 3 would tell us the additional effect of a 1 unit increase in looks, or this beauty measure, for a female. So there's whole papers that I've put up here, and I don't think that we talked about them specifically. This, watch, I have to put a trigger warning, I think, so I think they say some things that probably aren't the most PC. It's a Comedy Central bit, it's kind of old, so things age not the best, but it's pretty funny. So if you want to take a look at that, by all means. So it was an economist who actually did this, and what they find is, and they did a similar thing in this paper that I linked, but instead of using wages, they looked at interview requests. So I'll try to remember the exact, hopefully I'm getting this right from memory, but basically they took the exact same resumes, created LinkedIn profiles, and then they took all of these different like photos of individuals, and they had people rank them. So they had, I think I mentioned maybe last week, they do economic experiments here at IU. You can sign up for those. If you have questions about them, ask me. I Google where the link is at as well, because I don't know exactly what the address is, but you can find it pretty easily. You search IU economics experiments participant, probably find the link. And they had people rank these photos, and then they could kind of rank them based off attractiveness, right, in terms of how highly rated these people rank them. They then attached to these LinkedIn profiles different photos. Everything else in the profile, exactly the same. So same years of it, they went to the same university, same GPA, everything was identical. So they did a really good in these economic experiments. Yes, we can run these regressions and try to hold as much constant as possible, but there's also artificial ways we can do that. And this was one of them. So what they found was they then gathered the number of interview requests that each one of these LinkedIn profiles got. They applied to the exact same jobs. And what they found was, excuse me, that beta 2, right, was actually slightly negative, right? So that the effect of being female, it looked like there maybe was some discrimination going on from these firms, and that being female made it a little bit less likely that you got an interview, right? So the number of interview requests here was our dependent variable. However, the interaction term, when they interacted female with beauty, what they found that for men, right? So the effect of this looks, so this beauty measure on men would just be beta 1. It wasn't statistically significant, right? However, the interaction between the two, right? They found for females, this looks measure, this beta 3 was positive and actually increased the number of interview requests they got. So, I mean, this is not a good thing, right? This is evidence not only that we maybe have some discrimination going on, this underlying whether or not someone's female, but also that the looks shouldn't be playing a role at all in who's getting these interviews, right? It was the exact same resumes. And so we don't like seeing that there's statistical significance there either. So this was just kind of one application. I think here was kind of the nice graph they had with it. So basically for men, didn't matter what attraction, I shouldn't say it didn't matter at all. There's a slight increase, right, in that line of best fit. But I think I mentioned last class, what does this interaction term allow us to do? And I drew out like a scatter plot example. It basically allows us to estimate two lines of best fit for this relationship between our dependent and independent variables. So this relationship is the number of interview requests to feed, and then your attractiveness percentile. We can estimate a line of best fit for men and for women. Now, for men, we see yes, being in a higher attractiveness percentile, increasing the number of interview requests, but I mean, not much, right? In fact, statistically significant levels, I believe it wasn't statistically significant. However, for women, we can kind of see that line of best fit is much steeply sloped, right? There is a much larger effect. Okay? So I don't know, this is kind of a actual data, like an actual experiment that was ran that kind of tested this. So we've got continuous interaction terms as well. Those are going to be a little bit more difficult. We'll kind of dive into those here later today, or possibly not until next class. But we're going to kind of live in Stata and just rehash a lot of the things that we were talking about last week. So let's see here. We already looked at this stuff. Yeah, this is the one that I wanted to kind of take a look at. So we'll revisit kind of if we just do these interaction terms with dummy variables. We'll then kind of look at one where we have a dummy and a continuous variable. And then we'll think about, well, where is my, hold on. This should be, let me see, let me make sure I've got my default file, double check. So I want interaction terms. Should be one that has a few more slides. Let me see. It's not it. Well, I'll kind of do that one on the fly because I know that it exists. So we will first take a look at this one, right? So I've got this data set, which is the traffic stop data set. So it should be on Canvas there. So go ahead and open this up. Got traffic stop. Okay. So I've got my traffic stop data. There's a bunch of different variables in here. A lot of this is, identifiers for what the officer's race was. They assign different numbers. I don't remember exactly off the top of my head what number represents which racial group, but I do have it coded in, so we'll hopefully be able to figure it out. So here, if the result of the stop was a 2, that meant that the person was issued a ticket. So I'm going to generate this new variable, which is just a 1 if the traffic stop resulted in a ticket, 0 if not. I'm then going to create a bunch of race identifiers. So this is the driver's race. Here, 5 identified the driver as white, 2 black, 4 Hispanic, 3 was kind of our catch-all category. So I'm going to create all these variables. You can kind of see that that's happening here. There we go. I'm then going to create this interaction term between the driver's race and the officer's race. So we can identify discrimination using these dummy variables to see where different drivers of different races issue tickets at different rates. Now we can have some additional controls. However, we also might think that the officer's race might have some interaction, right? Or might have varying effects for drivers of different races, right? So there's a long line of literature, not like in the issuing of tickets, but just in general of race homogeneity and heterogeneity, how some races, within race, you might treat someone that's the same race of you differently than someone who's not, right? That's we don't want that, but right, we can investigate whether or not that's happening. So I've got the same thing here, but for the officer's race. So we'll use that officer's race variable and create these dummy variables here as well. Right? So we kind of run this regression real quick. Excuse me. I'm also going to create this interaction term. So maybe I think, okay, I'm going to just kind of make this to make it easier to start out. Just are white drivers treated differently by white officers compared to every other race? All right. So here I've got kind of this indicator for whether or not the driver was white and whether or not the officer was white. I'm going to create an interaction of the two. And I'll write this out here in just a second. So what I'm essentially thinking about, there we go. Sure this is focused. All right. So we're going to try to predict, right, whether or not someone is issued a ticket. And we're thinking about, we've got whether or not the driver was white, so the driver's race. We've got whether or not the officer was white, and then this interaction between the two. Yeah. Oh, not here. Thank you. Is that showing it better? Okay. Sorry, my perspective is the same as yours. So if we think about kind of plotting this, right? Well, when we just have these dummy variables, we said it's kind of like you're thinking about, let's say I wanted to estimate the relationship between, I don't know, even driver's age. So let's say one of the additional controls I have in here is the age of the driver, and then whether or not they were kind of issued a ticket, right? Well, if I have a non-white driver and a non-white officer, that kind of line of best fit is going to start out at beta 0. I could then estimate the effect for that group between age and whether or not a ticket was issued. So when we have these dummy variables and these interaction terms, it's really like we're just shifting the starting point of that y variable, okay? So I might have the exact same relationship between age and ticket. So I'm going to have something like, maybe it looks like this. However, what if I was estimating this relationship for a white driver and a non-white officer? Well, this would be 0. This would be 0. It would look something like this. Right? And if beta 1 is negative, it may not start up here. It may start down here, right? But these coefficients for these dummy variables are really just telling me, here would be kind of my line of best fit between driver's age and ticket. Here, this was for what? Non-white driver and non-white officer. This would be for white driver and non-white officer. What if I wanted for a white driver and a white officer? Well, that's going to be, this would be 1, this would be 1, and this would be 1, right? So I would have like beta 0 plus beta 1 plus beta 2 plus beta 3. Now, I haven't included any interaction terms with driver's age, right? This is just the driver's and the officer's race. So when I'm thinking about these kind of lines of best fit for these other relationships, when I use dummy variables and interaction terms, I'm really just kind of changing the starting point. Now, if these are negative, like I said, they might be higher or lower than the others, but basically you're getting all those coefficients added in. So we can identify kind of where the probability that a driver is issued a ticket kind of starts out, holding everything else constant for each one of these groups. So I think before, just to kind of solidify this here, if we were trying to just base off race, holding everything else constant, what's the kind of change? Or sorry, I want to do change. Let's say predicted probability of getting a ticket. Well, when I had white driver, white officer, that was kind of one category. That would be beta 0 plus beta 1 plus beta 2 plus beta 3. Right? All of these are 1, so all the coefficients get added in. What about for white driver, non-white officer? What we said there, it would just be the intercept plus beta 1. What about if we had non-white driver and a white officer? But we'd have the intercept. This would be 0. So this would be 0. Oh, but beta 2 would get added in. And then what if we had a non-white driver and a non-white officer? Well, essentially that was like our compare. That was the group that we left out, because if these are all 0, it's just the intercept. So by including this interaction term, when we have two dummy variables, and I think I showed you an example of this, and I have it in the code as well. It's just like what we were doing before. If we created kind of dummy variables for all these different combinations of officers' race and drivers' race, and then left one of them out. So the interaction term inherently leaves out what group? The one that would be a 0 for both of these dummy variables. So non-white drivers, non-white officers. Is this hopefully looking a little familiar, ringing a bell from what we talked about last week? Just a different example. So what we're going to do is run that regression where I've got, is the officer white, is the driver white, and the interaction of the two. So I'm going to also hold constant some of these other things. So I'm going to hold constant whether the officer and the driver were male or female. So I'm kind of like holding constant gender, holding constant the driver's age, officer's years of service, and then the reason for the stop. So this last one is a variable that has a bunch of different numbers associated with why the traffic stop occurred. Right? So by using that IDOT command, what is that doing? You remember? Might also apply to your problem set. I might ask you to include controls for the occupation type. So if you use the IDOT occupation, it's creating a dummy variable for every single occupation. And then including those in your regression and leaving one out. Here, if I'm using IDOT reason for the stop, any one of these, and I forget, the officer has to put it into their report, what the reason for the stop initially was, it's going to create a dummy variable for every single one of those. So if I'm holding that constant, it's like I'm saying 2 traffic stops, same reason for the traffic stop, officer had the same years of service, same driver age, same officer driver gender, but in one of the scenarios, the officer and driver were white. Now we can start thinking of what would the change in the predicted probability or issued a ticket is. Okay. So I'm going to run, what did I forgot to create my interaction term, right? So I'm going to run this. So I'll take a second. I think it's a fairly large data set, right? Yeah, 79,000 observations. So before we even look at these results, with 79,000 observations, what should be true about my p-values? They're likely going to be pretty small, right? And if they aren't, that means I probably don't have very good evidence that there's a relationship between that independent variable and the dependent variable. So if I'm looking here, okay, so I've got some pretty small p-values. I can reject most things. However, simply the effect of whether or not the driver is white, what's the change in the probability that they're issued a ticket? Well, holding constant everything else, if just the driver, simply from the driver being white, the probability they're issued a ticket is about 1.01 lower. Remember, this is probability, so it's like 1% kind of lower, right? Now, it's not quite statistically significant at our 1 and 5% levels, but it is at the 10. Okay? So, some evidence here that even if the reason for the stop is the same, everything else in the regression we hold constant, the fact that the driver is white, they're issued a ticket at slightly lower rates. Now, what's the interaction between whether or not the officer and the driver white? Well, first of all, I don't have any idea why this is the case, but the underlying effect, for whatever reason, I think this was from Texas. Actually, I know it was from Houston, this data set. And so, for whatever reason, white officers in Houston are issuing tickets at a higher rate, right? So that's pretty highly statistically significant. Now, what's interesting is if the officer is white and the driver is white, what's the additional effect, right, or change in the predicted probability that someone is issued a ticket? So it wouldn't just be that negative 0.01, right, from the driver being white and the officer non-white. The officer's white, they actually issue tickets to white drivers at about what? Probably 0.02 higher or 2% higher, right? In fact, that effect overshadows that effect of simply the driver being white. So this actually looks like, well, we actually may not have like discrimination going on here. We might actually have like that whatever, some combination of the driver and officer's race is causing officers to issue tickets to individuals of the same race at higher rates. Right? Now, I am not a sociologist, so that these are issues that for them to dive into, but we can identify that these issues exist, right? And once again, pretty highly statistically significant here. My p-value is 0.004. Okay. Any questions on this idea before we keep moving? Okay. Now, I don't think I have it in here because it would be an insane regression and take a very long time. But you could include interactions between every single race for a driver and an officer, right? Right now, we're kind of treating this as like non-white versus white drivers. Well, these different racial categories, like probably don't want to treat them exactly the same. Maybe police officers are treating individuals who are Black differently than Hispanic, et cetera, right? So what you could do, right? So this other method we had of including interaction terms was instead of creating the interaction term ourselves, we said if we take those two dummy variables and use this like double hashtag or pound signs, it'll create that for us. So we should get the exact same results as we have right here. Sure enough, we're getting those exact same results. Right? So just a different way of doing the same thing. Okay. Now, what you can do, and I'm going to see if this will work here. So let's see if I can remember what the syntax is off the top of my head. I think I can. So officers race, drivers race. Yeah, there we go. So let's say I were to do this. Let's see, I think this is going to work. Yeah. So this is insane. But before we look at the results, so if I use a variable and these officer driver race, remember we originally used those to create our dummy variables. So like the original driver race was like 1, 2, 3, 4, and 5. And that represented white, black, Asian, Hispanic, other. Right? If I were to use this double kind of hashtag, and I don't use the kind of officer or driver being white, but just the original variables, it'll create interactions between every single unique response to those variables. So essentially, it's creating all these different interaction terms. Now, the problem is, if I don't create them myself, I have to go back and remind myself, okay, what was the value of 2 for officer and driver race? So this would be the additional effect if the officer and the driver were a 2, which was if the officer and driver were black. And then here's the additional effect if the officer was black, driver was other, right? But I essentially have all these interaction terms that I can now include in my regression. Now, I'm not going to push you guys this far. I only ever expect you to do it with like 2 dummy variables, right? But you can do it when you have variables like this, and it'll create all of those dummy and all those interactions for you. Okay. So you notice it also includes the indicators for the different drivers and officers race. I think here it always is leaving out, you typically leaves out the 1 group, which tends to be Asian. I think it's just because, once again, it generally chooses the group that has the lowest number of observations. So that must mean that Houston has a relatively low Asian population here. It has the smallest number of observations. Cool. Any questions here? So I'm just kind of showing you a little bit. I wouldn't push you this far, but I do want to kind of give you the tools that if you start to get interested in this stuff, you could do something similar. Okay. All right. So what's a little bit more interesting. All right. And let's see here. This is not the data set I gave you guys. I gave you the NBA shots one. So let's open that up instead. So NBA shots, and I think let's just, for the sake of this example, we'll use the small one. Actually, which one did I give you guys? Yeah, I gave you the small one. Okay, I was going to say, I think there's a reason why. I think the larger data set, if we start to try to run some of these regressions, it's just takes forever. So I had this data set. I think we've looked at it a little bit before, but it's basically, here it's not just free throws. I think here I've got whether or not a shot was made. And I think this is all the NBA, I think 2000. Oh, let's see if it has the season in there. Not that it's matter, but yeah, 2014 data. It's got all these different shots by these different players, the time in the game, player attributes, whether or not, where is it at? Whether or not the shot was made, right? So we're going to start to use this data set. And the first thing I'm going to do is think about, okay, when I'm watching a basketball game, like I know that certain, I don't know if anyone's not a basketball fan. I'll try to set up, right? You have players who are like 5'5", and you have players who are like 7 feet tall. I was just watching some game last night, and one kid was like 7'4". It's ridiculous, right? So players of different heights probably have different skill sets. Right? So I might want to think about, okay, I'm going to try to identify these really tall players. So I'm either going to create this center variable, which is basically just identifying all the players who are playing what we kind of typically call this center position, or usually tend to be pretty tall. Now, I also have their height in inches. So I'm also going to create this tall variable. And what height in inches would be, 5 feet is 60, so 72. So this is what, 6'8". So anybody that's taller than 6'8", I'm going to kind of identify as a tall person in this data set. Okay. So I'm going to run that, create those two dummy variables. Okay. If I simply kind of regress, right, it looks like initially, oh, okay, height doesn't look like it's playing an impact on whether or not I'm making the shot. Right? So it's not statistically significant at any of our conventional levels, but I also don't have like any controls in there. So I had this thought, okay, well, I'm going to start to include a bunch of different controls. So I have what the player's kind of field goal or their shooting percentage usually is across the whole season. So I'm going to control essentially for how well they usually shoot, right? Also, different games have different attributes, right? If you go to like an IU game here, first few games of the season, there's a lot of empty seats. Actually, I don't know that. Typically, there's a lot more empty seats when they're playing competition who isn't as great, right? So maybe the attendance would impact the players who are playing as well. I've got, okay, what was the point gap of the game, right? If it was a close game, maybe the players psychologically are impacted differently. How close was the nearest defender? What was the angle that the shot was taken from? Was I on the home team or not? What was the player's age, weight, and how much time was left in the game? Taking the shot at the beginning of the game might have different psychological impacts than at the very end. So I've got all these different kind of controls. This is a lot more powerful of regression now. Now I'm saying holding constant all of these other things. So same field goal percentage, same attendance, the nearest defender was the same distance away, same shot angle to the basket, all of these things I'm holding constant. But now I'm going to try to identify, okay, what's the impact of being closer to the basket, right? So what is that relationship between whether or not I make the shot, right? Is that shot made? This is dummy variable 1, 0. And how far from the basket was the shot taken? So just inherently, what do you think that probability likely is? As you move further away from the basket, then more or less likely you make the shot. Less likely, right? It's a more difficult shot. Typically, if we look at like the averages. Now, I might also think, okay, I know that I have very different skill sets for my tall versus my shorter players. And it tends to, if you watch basketball, and if you don't, I'll lay it out. Taller players tend to not shoot quite as well. That's not always true, but on average, they tend to not be as skilled as shooters from further from the basket. So I think maybe this impact of shot distance, maybe it's impacting these taller players differently than it is the shorter players. So I'm going to create an interaction between the two. Now, once again, I could create this myself, or I could use this syntax in Stata where I use the double hashtag. It'll take that tall dummy variable and interact it with this continuous variable now. So now we don't have two dummy variables. We have one dummy variable, one continuous variable. So what are we doing? Now we're thinking about when I include a dummy and a continuous interaction term. Now I'm thinking about, okay, how does, is this still clear? Okay. How does shot distance and basically the probability that the shot was made, how does that shot distance impact it? However, I'm going to allow there to now be differences. So I have my Y variable is was the shot was made. I've got the thing that I was really interested in, which was the relationship between shot distance and whether or not the shot was made. However, I think that for this other group, we call them tall players, I think that that effect of shot distance might vary for that group. So I'm going to include an interaction term. Okay. So if I now think about what's the marginal effect of shot distance, right? If shot distance goes up by 1 unit for a non-tall player versus a tall player, what are the marginal effects going to be? Well, remember, when we say marginal effects, it's just like all your other econ classes. Marginal cost is what? The change in the econ degree. Total marginal cost is the change in total costs divided by a change in quantity, right? God, you guys better step it up here. I mean, we don't use this a lot, but I'm sure your other classes are, right? So anytime you're taking marginal, it's really a derivative. The change in whatever you want to know the marginal of, marginal cost, change in total cost, from what's changing, a change in quantity. Here, it's the change in our y variable, whether or not the shot was made, from a change in shot distance. So if I take a derivative of this function in respect to shot distance, for someone who's not tall, it would simply be beta 1. All we're doing with these linear regressions are estimating marginal effects. Why do you want to do this? Well, because if you have price quantity data or you have cost quantity data, what can I do? I can estimate a firm's marginal costs. In fact, there's economists that spend like their lives doing this, usually in a much more complicated way, but like they'll look at not only firms' costs, they'll look at like import costs and like run these regressions. So here, what's the marginal effect if it's a tall individual of a 1 unit change in shot distance? Well, it would be beta 1. But now if they're identified as tall, this dummy variable is a 1, you'll also get this additional effect, which is beta 3. Now, this is the change in the marginal effect. So this is telling us something about the slope of that line of best fit. What about the intercepts? Well, where would shot mates start out at for someone who's not tall? Simply beta 0. I don't remember if this is positive or not. We'll model it like it is, and we'll see if I'm right. But, right, what would it be for someone who's tall? It would be the intercept plus beta 2. So kind of similar to when we had two groups of dummy variables, or two dummy variables. We're still getting a different starting point for our two groups. The intercept is still going to be at a different point. It's just now, for those individuals who are not tall, right? What's the effect of a 1 unit change in shot distance? It's simply going to be beta 1. And what's the effect for some marginal effect of a 1 unit change in shot distance for someone who's considered tall? Well, here for a second, we're going to assume beta 3 is positive. So that would mean the slope of beta, not 0, beta 1 plus beta 3. We're now able to identify differences in slopes for these two groups. So not only a difference in starting point, but a difference in slope. Now, if beta 3 was negative here, what would be true about my slope? It'd be a little bit flat. Right? I'm assuming it's positive here. I think that it's positive just based off of the variables. I'm thinking that the effective shot distance is going to impact tall players more. I don't know if that's the case, but I probably shouldn't make these assumptions going in. We have the actual data. We can figure out whether or not that's true. Okay. Any questions on this idea? So if I asked you for the marginal effect of a continuous variable with your dependent y variable, but what is it for two different groups? That interaction term coefficient is going to tell you that difference in the marginal effect. So if we look back at the data, right, I'm going to go ahead and run this regression. And it looks like, okay, here's my three variables. So here's that tall dummy variable. Here's the continuous variable, which was shot distance. I think this was measured in feet, if I remember correctly. And then here was the effect, the interaction between being tall and that shot distance. So it looks like, simply for being identified as a tall player, even if the shot distance was 0, what's the probability? Is it higher or lower that they make the shot? So even if shot distance was 0, what's predicted change in the probability they make the shot if they're considered tall? Negative 0.03. So actually, for these taller players, I actually didn't quite have the right drawing, right? Because when I'm thinking about wrapping this out, well, beta 2 here was actually negative. So it was the case that this line of best fit, so here, beta 0 plus beta 2 would actually be below that for the, so this was non-tall, and this was tall. But I was assuming beta 2 is positive. I run the regression, I see it's actually not. So here for my tall players, they're going to actually start out when that shot distance is 0, they start out at a lower point. Probably make the shot from being 0 feet away from the basket is actually lower, which is kind of counterintuitive. I wouldn't have guessed that. Right? However, the marginal effect, so the slope of that line, what's the difference? So for shot distance, oh, I was drawing these all as positive relationships. What should I have been drawing them as? Well, the effect of a 1 unit change in shot distance on the probability to make the shot is actually negative. So if that's negative, I was actually going to be thinking about, okay, here was just the effect of shot distance on non-tall players. So it's what, negative 0.001. So this was kind of my non-tall group. Looks something like this. Okay. Now, what about for the tall group? Well, I'd still have that base level impact of shot distance that was negative, but for a tall player, shot distance, the interaction term is actually positive. So what would the slope there between shot distance and the probability to make the shot actually be? So 0.001 plus, sorry, negative 0.001 plus 0.002. Here's a really weird one where I actually get that for these tall players, looks something like this, right? So I wouldn't have guessed this. Now, there could be some omitted variable bias here that we don't have some other factors that matter. We haven't talked about selection issues, but we probably want to think about that as well. We'll kind of dive deeper into those. But I like this example because it's like, sometimes you might have what you think is intuitive, like you think you know what the results are going to be going into it, and then the results are counterintuitive. But that's because when you're watching a basketball game, you just see the player taking, you don't think about all the other factors that are related in that shot. Here with our regression, we're controlling for all those other factors. So you're actually taking things where when you watch something play out, not just in a dumb sporting game, right? When you watch things play out in the real world, we only observe what we're seeing. We don't think of like holding all the factors that are going on constantly. Our regressions can do that, right? So here's one where it's kind of maybe a little bit counterintuitive. Now, I also will make one point here. Notice the predicted probability that the shot is made. Maybe it is increasing for these tall players, but this point could be at a shot distance that doesn't even make any sense, right? So it might be that like the shots we observe, the tall players still have a lower predicted probability of making the shot, right? Because we never see shot distances that are out that far, right? We got to think about when we're plotting these, right? What are the actual X values we see in the data set? Just because we have these two lines that are going, going to converge at some point. For example, let's say the shot distance was 300 feet where they cross. Basketball, I don't think the basketball court is 300 feet in length, so it doesn't make any sense for us, right? Excuse me, we'll never see those crossed. So we're going to be a little bit cautious when we're, thinking about, well, tall players will make it at a higher, well, no, we'll never see values that high. But this does highlight we can estimate differences in that marginal effect and that initial starting point for this group, or between these two groups. Any questions over this before we keep moving here? Okay. So now I should be cautious here, because if I'm looking at any of these variables, which of these can I say that there's a statistically significant difference between shot distance for tall and non-tall players? Well, what's the additional effect of shot distance on tall players? That's my interaction term. What's true about its statistical significance? P-value is 0.3. I can't really say there's any statistically significant difference here, right? So even though I can graph out what those actual values are, I've got like a confidence interval that would overlap for all of them, right? I can't say this is statistically significant at any level. In fact, I can't even say that shot distance has an effect here. So it must be like, I must have some omitted variables, because we inherently know shot distance probably matters, but there must be a lot of other important omitted variables that we still aren't including, right? So just like before, if we have omitted variables, that's going to include bias in every single one of our estimates, not just the estimates of that dummy and continuous variable, but also the estimates of the interaction term. And we won't dive into it, but there it gets a lot harder to disentangle what the bias is there, right? But we know it exists. That's all I want you guys to know, is that it would exist. Okay. Let me just think if there's anything else I want to say. So I think I did the same thing, but I did this for the center variable, just to make kind kind of show. I'm still getting kind of statistically insignificant results. I get similar signs, but you could do this for any dummy, any continuous variable that you were interested in. In fact, I can do this for, this is like looks similar to like our beauty gender one, right? So dummy variable, continuous variable interactions, we can do those. Any questions on this before we keep moving here? Okay. So let me see here. I think I've got some other mate height stuff that I wanted to do, but I'm not sure it's going to let me open this unless I drag it out here. So let me see if it'll let me open this file. Don't think it will, but. This is a do file. Let me see. Now I can pull my laptop up and try to get this going, but let's do. Let's see if that works. Oh, let me see here. So go back. Awesome. So this is the one. Oh, it didn't have it either. What file was this in? Well, I can just do it off the top of my head, I think. Let's go. I've got that mate height. So let's go to. And so the next thing we'll look at is kind of this mate height data set. So open this up. Don't save. Okay. So here I've got kind of a small data set. Not a lot of controls here. So we're going to take these regression results with a grain of salt. But it is kind of an interesting result that we can look at. So we've looked at dummy variable interaction terms. We've also looked at dummy continuous variable interaction terms. We can also look at continuous variable interaction terms. Right? So what's that going to look like? So maybe I'm wanting to do something like, actually, no, this isn't what this example is. We're going to keep doing dummy continuous. So let's say I want to try to predict mate height, right? So this is like a data set of a bunch of different married couples, what their height was. And I'm thinking about, this is the individual's height. And then I'm going to include here, let me see if I can remember what it's going to be. Well, this is good for data. So this is a good point to make. So inherently, what do we know is true about male versus female height? On average, males are taller, right? This is not a biologue. I'm not blowing your mind here. So I've got this data set. So this is like a good, just like general how to use data sets. I've got this height, mate height. I also have the gender of the individual. Well, I can't remember if 1 is male or 0 is not, right? So what's one thing I could do to kind of figure that out? Well, if I sum that height variable, right? If this gender variable is equal to 1, oh, how's it spelled? It's capitalized. All right, so we'll sum capitalized height if gender is equal to 1. Okay, what did I do there? Oh, come on. So I'm going to do page up. That's a good shortcut also. If you ever, so let's say I made a mistake here, right? I accidentally put 2 parentheses. So instead of typing everything out again, if you have a page up button, and sometimes like on this one, I have to hold control to use my page up. Like it depends, every model is a little bit different for a laptop. But if you have a page up button, if you hit the page up, it'll put the last line of code that you kind of put in there. Well, actually, I want a couple, but right? What I actually wanted this to be was capitalized. And you can actually use that and go higher and higher up to what code you use. So you can go back even further than 1. Except for now, I want to go page down. Oh, Now I want to go page up. There we go. Right? Okay. So I want to get rid of this parenthesis. Now I don't have to retype this all out. Right? So that can be kind of a nice, useful thing when you're working through these. So I'm going to do the same thing, hit page up, but now I want to summarize this variable if it's equal to 0. Now, when you're doing the problem sets, you have to turn your code in. You can use the command thing here, but just make sure you're copying and pasting your code into that do file that you can upload, right? And so that you have your results saved. Remember, nothing in this command box gets saved. So I look here, oh, which of these groups, what does a 1 identify, male or female here? Well, the average height, if gender was equal to 1, was 70 inches. Average height, if it was 0, is 64. So it must be that my 1 group represents males. Right? So what we're going to do is include this male dummy. Right? We're also going to say, okay, look, maybe when males are making their choice for someone they want to be with, maybe they care about height more than women do, right? Or vice versa. So, right, I might interact with that height variable. So the taller I am, like, this is maybe stereotypical, but like, you know, if you walk around, you don't see a lot of 7-foot tall, I think, or even don't tend to see males whose mates are a lot taller than them. That's not always the case, right? But on average, right, we can, in fact, let's see if that's true. I shouldn't just be making generalities, right? We've got the data. So what can I do? Well, I can sum this mate height variable if gender is equal to 1. And then I can do the exact same thing if it's equal to 0. Oh, what do you know? Males tend to choose a mate who's shorter on average than females, right? So maybe we think that there's also an interaction, right? It's not just that men typically choose someone who's shorter than them. It's the fact that on average they're taller. So inherently, more women are shorter than them. So maybe there's this interaction between own height and whether or not I'm male. So I'm going to run this regression. In fact, scroll down here so I can save a bunch of this. So where was that mate height? We go all the way back up here. I'm going to copy, paste this. So we have that data set. And then I'm going to run a regression where I'm going to try to predict mate height using the individual's height, also whether or not they were male. And I'm going to create an interaction between those two variables. Okay. Now you could use that double hashtag by all means if you want to. I just think it's easier to name the variable so you really know what it represents, and it makes the regression output a little bit easier to look at. So I'm going to generate this interaction term. Oh, it didn't find. Oh, why? Just to remind myself, that gender variable, we said it was a 1. They were male, 0 if not. So I'm just going to rename it to make that a little bit more clear. Now I can create my interaction term and then going to run my regression with a control for height, male, and the interaction of the two. Okay. So I run this regression, right? Now I can start to think about plotting these out. Okay. So I'm going to write these down real quick and then we'll kind of go away from here. So what? Beta 3, the interaction was what? Negative 0.28 approximately. On male, it was 10.99. And on height, it was 0.67. Okay. So we obtain these regression results. Sometimes it might help to write out what your regression equation looks like and now what was each one of those estimated coefficients. So if I'm now thinking about plotting this out, if I wanted to predict mate height based off of the individual's height, but I think that that relationship might vary between males and females. So here's 0. So if I'm thinking about where would, at a height of 0, where would the predicted mate height be for males? Well, it would be, well, actually, we'll do females first because it's probably easier to think about that. If we did the intercept for females, where would that be at? you're going to need one more piece of information here that I left off. So what would the predicted male mate height be for a female who is 0 inches tall? Kind of a weird interpretation, but. So 0 inches tall, they're female. The predicted mate height would simply be my intercept, right? So whatever that 0 group is, that intercept is kind of their starting out. Well, now we know that in our scatter plot of data, are we ever going to see anybody who's 10 inches tall? No, right? So we know our data is all going to live kind of over here, right? People aren't 20 inches, tall. Right? So we're going to try to estimate a line of best fit. We know that all the data is probably going to be somewhere over here, but for females. So what's the effect of being 1 inch taller for females? That marginal effect would simply be what? So if they're female, what happens to this? This would become 0, so that doesn't get added in. A 1 unit change in height will change the predicted mate height by simply beta 1, right? Or 0.67. So we know that for females here, the relationship between their own height and mate height is going to be 0.67. So for every inch taller that a female is, their mate on average is about 2/3 of an inch taller. Okay. Now, obviously, we have a lot of limited variables here, but this is the general idea. Okay. Now, what if I was trying to think about where does the predicted mate height start out at for males? So if they're male, where would the predicted mate height start out at? Well, you'd have the intercept, but you'd also have beta 2, right? So 27.7 plus 10.99. So what? That's going to be approximately 38.7, right? You're just adding up those two coefficients. So we know that the predicted mate height is going to start out a little bit higher than males. Now, what's the slope of the male line of best fit between height and mate height? Well, the marginal effect of height is going to be 0.67, but for males, there's an additional whatever beta 3 is. So beta 3 is negative. So what's true about the slope for that relationship between own height and mate height for males? It's going to be what? If the additional effect is negative, that slope is going to be flatter, right? Because the total slope for males is going to be beta 1 plus beta 3, right? So for females, it was just that beta 1 value. Now for males, that slope is going to be what? Beta 1 plus beta 3. So if I'm adding those up, it's going to be just what? 0.39, right? So it's going to be a little bit flatter. So for every additional inch taller that a female is, they choose a mate that's about 2/3 of an inch taller. For every inch taller a male is, they choose a female that's only about 1/3 of an inch taller. Right? So this effect of being 1 inch taller between males and females here, the difference is about not quite half, but close, right? We're getting to it's almost double the size. Now, this is a dumb example about mate height, right? If we're thinking about, well, what's the impact of an additional year of education on income or something like that, we care quite a bit that these differences are about twice as large for men or twice as large for females as opposed to men. So that's kind of how we would take those interaction terms, plot them out, think about the relationship that exists between males and females and the varying effects from some X variable here. We just chose the effect of height on mate height. Okay. Now, can I say that own height has a statistically significant different effect on males than it does for females here? Well, what would tell me that? the statistical significance of my interaction term. Okay. So that statistical significance of my interaction term is 0.01. So I can reject at my 10 to 5% level, not quite the 1, but we're pretty close, right? So this is pretty strong evidence that there is a statistically significant difference between the effect of own height, right, on mate height across males and females. Right? So we would look at, does this marginal effect look at varies between the two groups? You would look at the statistical significance of the interaction term. What's another thing that we could look at? So let's say I just ran this regression of mate height and male, but I didn't include the interaction term. By including the interaction term, what do we know is definitely going to increase? Well, I'm adding another variable, so what has to go up? So I know my R squared is going to be larger. So what can I do? What do I instead of looking at my R squared between these two regressions? I might want to look at my, adjusted R squared. So if I run this regression, I put generate. I'm talking and trying to type here. Here we go. Reg, right? Well, my R squared goes from 0.50 to 0.51. Okay, so it definitely increased. But notice my adjusted R squared, accounting for how many variables I'm using to make these predictions, 0.499 to 0.51. So my adjusted R squared up by including the interaction term, that's a second indicator that I should be including the interaction term. Now I can explain more of the variation in that Y variable. So the statistical significance on the interaction term, difference in that adjusted R squared are both good indicators that we should be using the model where we include the interaction term. Okay. Any other questions on that one before I keep moving here? Okay. So we'll hold off on continuous here. Let me see. I've got something sitting out here. And let me hide this for just a second because I can't remember what this is. Okay. What's today's date? 5th. This in just a second here, so let's go. Save that. I want to look behind the scenes real quick before I show this to you guys. So I've got 3 different questions. Let's do 7, I'm now going to publish this. I'm going to throw on the home page so that we can kind of take a look here. So I still like to reward participation here. I didn't quite have this ready to go, so thank you for bearing with me.